Okay, probability and its application. So this is now, it's not session 6, so I changed the order a little bit. So, but as promised, we're going to talk about screening tests today. Screening tests basically is it's like the preliminary brother of a diagnostic test. The principles are kind of the same, but with screening tests, you deal with varying prevalences, which is particularly interesting in evaluating differences between sensitivity and specificity, a very test-specific metric, whereas positive predictive value and negative predictive value is basically associated with the prevalence of disease, so how often a disease actually is present in a population, and then intertwines with sensitivity and specificity. Because if you test in a population where you know it's a very common disease, and you have a test that tests with a certain probability correct, it's in the end of the day after the test, your probability of having a correct result is going to be higher if you know that the presence of the disease is more common in the population, right? So only what's common is actually really common as an outcome. And this is also the principle that is used for various applications with mass screening, for example. When we had COVID, when we were dealing with COVID in a more acute setting, screening was really key. And with screening, there was additional the problem. You had possibly a lack of tests, and you needed to be very smart. You didn't have the tests, you didn't have the time. So there were a lot of factors that came together that you needed to utilize probabilities to really draw inferences of how common this disease is. One aspect that actually became very popular, became very much pushed into the spotlight was pool testing, where basically you only test into smaller pools of your overall population. You quantify the probability of the disease being present in a pool, and then you extrapolate that probability from a smaller pool to a greater pool. By that, you limit the amount of resources that you need to screen the entire population, but you yet have a very good estimate of the prevalence or incidence. It was COVID, it was, well, at times it was actually prevalence. Who knows the difference between the prevalence and the incidence? Yeah?
Prevalence is how many people in a total population at a given point, and incidences over the course of time, how often will it?
Correct. Very good. Very good. That's exactly the definition. So basically, the difference is you're basically cross-sectionally looking at one point for a prevalence. So it's presented as a percentage. So it's usually quantified in diseases that have a certain timeline that are around for a certain time. So for COVID, for example, people had COVID and they had COVID without knowing it. So you almost can talk a little bit about prevalence, but basically, usually you do it for chronic diseases. So you want to quantify the prevalence of diabetes in the population. And I kept on talking about prevalence of diabetes last time with probability distributions. So you're quantifying this as a percentage of the population. That's a prevalence. When it comes to incidence, an incidence is the occurrence of a disease newly in a population over time. So it has a time component to it. So it's basically, you have an observation period and you count over with what frequency this time, this new condition will occur in this population. So it's a new onset of a disease over time. What you also need to do then with incidence rates, you are basically expressing it also as a rate, and a rate is also the occurrence of a new disease over time. So it's usually you are quantifying it with an additional metric for time. The most common way to depict it is usually patient years, population or citizen years, person years. So it's count per person years, and you have the occurrence of an observed population. You quantify in the denominator what the population looks like, how many people were in the population. You're dividing that count of a new disease by the population over a certain period of time, and then you're standardizing it to a certain timeline, which is usually it's a year, or it can be a month, can be a week, and you're standardizing to a certain fraction of the population. So often you will see something like count per 100,000 person years. So that implies you have a count, a new occurrence of a disease within 100,000 patient and person years. That basically implies that you have 100,000 patients over 1 year. So you're bringing it down to the denominator, with the denominator dividing by the population. You get a count per one person, and then you multiply it by 100,000 over the period of a year. That gets you to this standardized metric. So you always standardize it to a metric you're comfortable with. Okay, but this is the difference between prevalence and incidence. So for positive predictive value and negative predictive value, we're talking about prevalences for the sake of not confusing the discussion. Then we have the properties of probability. Then we talk briefly about conditional probability, also not in too much detail because it becomes quite complicated. But positive and negative predictive value is basically that union between sensitivity, specificity, and the prevalence. So Bayes' theorem is basically underlying conditional probability, and you will see why. Good. Okay, so why is this important? Let's assume we have a screening test that is correctly positive for 100% of cancer patients. The prevalence of cancer is 5 per 1,000 per year. So it's essentially 0.5%. If the test is applied to the general population, what is the probability that an individual testing positive has cancer? It's a good question, right? Can you actually say that with the data provider? But it emphasizes already how important that actually is, because what you have a test who tests every cancer patient, but it doesn't tell you what it does with patients that don't have cancer. It may test positive for people that don't have cancer, and you don't want to misdiagnose individuals. And there is a conversation we're going to get very deep into, and not too deep into, but we're going to touch upon too, because there are a lot of diagnostic tests that are being conducted on a regular basis where there are strong opinions. It shouldn't be done as frequent. It shouldn't be done as often as it's currently done, because it has ramifications. If you assume that individual now has cancer, and you start considering surgical methods to basically get against the cancer, that has ramifications on a whole different level, right? So it becomes a very problematic conversations, and really the only way to get a solid handle on that is to employ principles of probability to basically understand what is the probability and what probability to be wrong in not diagnosing that cancer am I willing to accept for my population. And that is a tricky question, as you can imagine, but it's not a simple question. So the answer is that you don't really know. You just don't know what that probability is. Because if you're employing a test with a prevalence of 0.5%, you have 9,995 healthy people. So you don't know what it does with these healthy people. That's the problem. So ideally, a test would be 100% accurate. That means 100% accurate means only if a patient has cancer, you have a 100% probability this individual will be diagnosed accurately. This is 100% not the case. All diagnostic tests fail. They don't fail, but they're inaccurate. They're chronically inaccurate. As an example that really blew my mind when I was exposed to it, when I heard about it the first time, you know that when you have a myocardial infarction, heart attack, right? Everybody's going to think of, yeah, just write an EKG, right? You see on the cardiac activity of the heart, you see that the individual has a heart attack. It's actually very characteristic. If you have a characteristic pattern in your cardiac activity, in your electrical cardiac activity of on the EKG, it's very characteristic. You can't misdiagnose it. It's like med student first year can diagnose that. It's that simple. The problem is it doesn't always present that way. The probability of an individual actually being correctly diagnosed with an EKG for a heart attack, knowing nothing else, so no symptoms, no history whatsoever, is somewhere in the realm of 65%. So that's how inaccurate medical diagnostic can be, right? So that's why it's so important. What you will hear in med school is the very first thing they tell you is like the most important thing is like, did you ever have that before? What's your medical history? Because that is really indicative. That's the strongest predictor of a disease occurring. So in reality, most tests make mistakes. They make wrong decisions in one direction. So they give you an incorrectly positive test. That's a problem. That's the individual who think he has cancer. Okay, let's get the operating room ready. You have false negatives. You have incorrectly negative tests. This is like, no, you're fine. And you send the patient home. Both problematic. Equal, not even sure equally, but they are very problematic. And this is why this is so important as a basic. So the performance of a test in addition to that depends A, on the test per se, and then B, also on the population you're actually applying it to. And for that, you need a reference method. And this is the next problem. The reference methods are quite poor because when it comes to a heart attack, for example, the reference method of the only really definite reference method is an autopsy. So in the end of the day, there is no absolute truth. And that's the problem. That's really the problem. It's like I come, so we did, example from my world is like I work with dialysis patients. I work in the field of nephrology. So one of the big problems dialysis patients have, they have a loss of renal function. They don't excrete volumes anymore. So that means they accumulate this volume. This volume distributes then into interstitial compartment, extracellular compartment, intravascular compartment. So it can be really bad for the patient. It can be as bad that you get swollen legs. That's in an advanced stage. You can get lung edema. Patients have troubles breathing when they're fluid overloaded. So it's really, it has deleterious consequences. So now, obviously, the whole nephrology world is interested to estimate volumes and to estimate what is fluid overload. The problem is nobody knows. Nobody has an accurate, 100% accurate tool to diagnose what is a normal state of hydration, because even in the normal population, you all have healthy kidneys, I hope. So you basically, with a healthy kidney, you will have variations in your fluid overload depending on your food intake, your salt intake, the time of the day. Because if you stand the entire day, your feet are going to be more swollen. Your blood is going to be somewhere residing in your lower extremities. So there are variations in healthy individuals. So now, let alone dialysis patients who can't even have the normal function of the kidney. So now you want to estimate volumes. You can't really estimate volumes. And what we found out is that the method, and this is where we're going in the realm of biotechnology a bit, there are methods where you apply weak currents to the body and you utilize an estimate of the resistance to this weak current to employ multi-compartment models to estimate the amount of fluid inside of cells and the amount of fluid outside of cells. And you can utilize this to estimate volume. So now we did experiments like that, and we had our quote unquote silver standard at this point, and we wanted to compare it to a gold standard. Only to find out that our method actually was more of a bronze standard. The reference method, the gold standard, was actually more of a silver method, and the gold standard would essentially, yeah, hard to say what the gold standard could be. So there are methods which you can do with dead people. So with bodies, you can basically cremate them, make them ash, and then you kind of can deduct the difference, and that would be the volume. You can't really do that. At least you will have a hard time getting this through an IRB. So, so we have now essentially no gold standard to estimate volume. And even the gold standards amongst themselves, so you had different gold standards for different volume compartments. Even the gold standards were like inaccurate. Everything is inaccurate. Like literally everything is inaccurate.
What about body size? Measure everything.
Well, hypothetically, body size, but how?
Legs, like swollen part of the swollen part.
But how do you measure the weight of the leg, right?
Not weight, but like 8 centimeters.
Yes, a swollen leg, and yes, actually one of the ways how we tried that. So you would think that, interesting question, because we did literally that. We measured the circumference of the calf, and we measured fluid status in the calf, and we used this as a marker of fluid overload. Actually, the point, actually. The problem is, there's a difference if the patient comes to the dialysis clinic after a day of walking, or if the patient was sedentary, just lying on the couch the entire day. So it's, nothing is accurate. And that's my point pretty much, right? It's like,
To take out the liquid.
take out the liquid?
Yeah.
How are you going to do that? With drugs?
Yeah.
Well, but the patient has no kidney, no more kidney. No more kidney. You don't get this out, right? What you can do is,
on dialysis.
yep. So with dialysis, you remove fluid, but you also can't remove fluid indefinitely, right? It's like usually when you remove a certain fraction of the patient's volume, the patient's blood pressure will decrease to an extent that, yeah, you have consequences to that removal. That's actually one of the research projects that we have conducted. How fast can you remove how much fluid? So it actually, if you remove it too fast, too quickly, and too much too quickly, you basically it comes to a hyperperfusion of organs. So you lower the perfusion into the organs, which basically can have effects on the cardiac muscle in particular. It's called myocardial stunning. Chris McIntyre from the UK studied that. Well, excellent point. Okay, so no gold standard. So we have no gold standard. So now there are a couple of ways how to now essentially study that. Let's assume this scenario here. Let's assume two different settings, two different populations you're basically studying in terms of chlamydia infection. You're studying them in two different settings where you basically have a private practice where it's quite rare that you have an individual coming with a chlamydia infection. Then you study it again in an STD clinic with high prevalence of chlamydia infection. So you have these two different groups, and this is now the aspect. So you have a test that is equally good in both populations. But if you employ it in different populations, you basically have a substantially different positive predictive value. And that's a problem. The negative predictive value remains good enough because the way this is calculated, and that actually would be, yeah. So the positive and negative predictive value is calculated basically as positives amongst those that have tested positive. So that would be 294 divided by 315. So that would be those that tested positive and do indeed have the disease. So you basically, this is a so-called contingency table, a 2-by-2 table. The way you will see this presented in the realm of epidemiology, it differs a bit with different application cases. You will always see disease And that's kind of your gold standard, because chlamydia infection at the end of the day, the definite diagnosis is done with microscopic tests and PCR tests. So basically you have the actual prevalence or the actual disease as an outcome in the columns, and you have the actual test on the rows. So the PCR test is here testing chlamydia infection. So what this basically means is you see with positive predictive value and negative predictive value that there are tremendous differences between the diagnostic possibility to say an individual is actually positive or not, and the prevalence of a disease actually plays a major role in this. And why does it do that? So you're basically distinguishing between event as an outcome. We know that probability is the rate of an event happening. So this positive and negative predictive value is basically a product of the prevalence, but also the diagnostic capability of a test. And this is where sensitivity and specificity comes into play. So sensitivity is the probability of a positive test for individuals that actually really have the disease, where that's the cancer patient that is being tested. So if you have 100% probability that individuals with the test are being positive, so that's a very sensitive test. So a specific test, specificity is basically the probability of a negative test of somebody that has not the disease actually really having a negative test.
But basically it is the same, right?
Yeah. Think of this. You have here patients with chlamydia. You have patients without chlamydia. You have patients with a positive test, and you have patients with a negative test. Specificity and sensitivity. So this would be specificity. These are those so-called true negatives that do not have the disease and do not test positive. The denominator of this would be 700. So these 679 and the 21 that are negative. And so this is basically the group of interest. So they tested positive. So they are false positives. So basically specificity is calculated as true negatives divided by true negatives and false positives. Sensitivity is the true positives, those that really have the disease and those that test positive, divided by true positives and false negatives. So these are the ones that actually have the disease but are not testing positive. So they are.
And we don't get the same.
You get a different result, and that is the problem. So
What you think should be the same, right?
no. And I will show you in a second why. Absolutely not. Because we're getting now to diabetes. And you will see now in a second why it is not the same. Let's assume we have type 2 diabetes. This is highly prevalent in older obese patients. Good. The gold standard requires oral glucose tolerance testing. So essentially what you're trying to do, you have a fasting patient, you give them a glass of glucose solution, which tastes terrible. Those of you who have ever done it, it's really not good. You drink that in one shot, and you do glucose measurement over a period of time, where you basically see whether that glucose load actually initiates an insulin secretion, and that insulin makes that good glucose disappear in your muscle cells or in whatever cells is using it. So you basically this decline of glucose will be indicative of presence of diabetes or not, because type 2 diabetes comes with insulin resistance. That means your insulin is high, but that glucose that you have loaded is not disappearing as fast because your muscle cells are like, oh, glucose again, not that insulin is like, I'm not reacting. So basically you create insulin resistance. So by that, the decline is gonna be flatter, so less decline. And thereby you can say, okay, patient is most likely diabetic. So now you have various other ways how to diagnose that. One of them is a screening test. Screening test is the fasting glucose test that I mentioned earlier. You have a patient fast for 12 hours, comes in the morning, you take a blood sample, you measure the serum glucose, and you know what that glucose is supposed to be. If it's greater than 100, it may be prediabetes. If it's greater than 120, it may be diabetes. And the higher it gets, the more likely that patient has diabetes. So now, let's assume we have now blood sugar, fasting blood sugar of 20 diabetics and 20 non-diabetics. So you basically have here low blood sugar and high blood sugar, equally distributed. And now you want to diagnose it. And you have now a threshold which you're using to diagnose diabetes. And I love this example. That's a really good example because essentially, let's assume you cut this threshold through any arbitrary value. Let's say it's 100 milligrams per deciliter. So you have your diabetics and non-diabetics. You have 17 diabetics that were positive and 3 only were negative using your threshold. In the non-diabetics, it was 14 versus 6. So you end up with a sensitivity of 85% and a specificity of 30%. If you are now increasing your threshold, you basically increasing the thresholds. You're diagnosing less diabetics as being possibly diabetic and more diabetics as being possibly non-diabetic. You're basically increasing in terms of specificity, you're increasing now the number of non-diabetics that are positive but don't have the disease. And you are increasing the number of non-diabetics that are indeed diagnosed as being non-diabetic. So the specificity is high. So again, to your question, is it the same? That is what the key is, right? So that threshold determines how sensitive and specific your test is. And that's why I like this example, because it illustrates it quite well, right? So this is that trade-off you're dealing with whenever you're looking into decision making. And this is, it depends on the test. If it's a fasting glucose and you're taking a blood sample and that doesn't cost you much money, it's like glucose testing, what does it cost? Like $11, $12 or so. So if it's a cheap, easy test, make it sensitive, make it super sensitive. I'd rather have that patient come in a second day, has to take off another day and I do an oral glucose tolerance test with them, also not expensive. Let's do a second test, let's make sure. Good. If you consequently to a test, you prescribe him then a regimen of a medication that costs somewhere in the realm of like 50,000 a month, you may want to make sure that this patient really suffers from the disease, or you have a patient having to undergo surgery. You want to make really, really sure that that individual has indeed the disease. That's why what you do in medicine is that you evaluate differential diagnosis. You make sure that you're really coming to a decision that is sound on all ends. Okay, that's the trade-off. There are statistical methods to evaluate these trade-offs. One of them, for example, is Youden's index, which is mentioned in the paper that I've uploaded on Canvas. Youden's index basically creates a balance between sensitivity and specificity. Can be used as well for various purposes, but basically there are various ways to do that, and it really comes down to the use case in many cases. It's really what are you using it for. So the problem that you have now is you don't have a gold standard. And out there in real life, you don't have this line separating diabetics versus non-diabetics. There's like a random person coming into your practice saying, okay, so I want that measured. I want to know whether I have diabetes. You don't know this. This is something that you get as a recommendation from guidelines, but you also don't know this. So this also varies, right? So both of these lines are basically interchangeably varying. That makes it problematic. This is why prevalence is important. Because the prevalence, that's this line. So the prevalence shifting will basically help you to come to that decision, whether you essentially looking at a diabetic patient or a non-diabetic patient. So that's the real life, right? It's like, it's a mixed bag. It's a mixed bag of chocolate. So no color, no label. You don't know whether that individual is diabetic or not. You will just simply not know. So now you have screening tests, and this is usually derived from studies. Large studies, like the one that I have added on Canvas, that is basically, and I will talk about this in a second then, and explain the concept to you, but that's basically a test we have studied for the last, 17 years. I've been involved in research on the salivary nitrogen dipstick. And so we have done various studies in different populations, and you find those thresholds, and based on those study results, you determine thresholds that kind of are reasonable in the context of your use case. And so it is for blood glucose. So if the American Diabetes Association gives out a recommendation for fasting blood glucose, they have done a lot of research to come up with this level. So there's expert opinions, there are studies, specific screening studies. There are large studies and thousands of patients that have been conducted, making sure that these thresholds that are recommended are really valid thresholds. Yeah. Low cut point. Yeah, so it's this trade-off, whether you take a high cutoff or a low cutoff. Cut point determines how many subjects will consider as having the disease. Lower cut points result in more false negatives. Higher cutoffs in more false positives. If you remember the 4x2 table, that respectively higher cutoff points, more false positives, ergo will create more or a lower specificity. So you're more likely to misdiagnose. For sensitivity, the other way around. So now you want to bring this somewhat after you have determined now, based on your studies, you have determined your cutoff. And now assume it's the same cutoff for any population you're looking at. So now we're coming towards, what does prevalence have to do with anything? So we talked before about the chlamydia. If you conducting a test, two equal tests in two different populations, one was a high prevalence, one was a low prevalence. In the end of the day, the post-test probability of this individual having the disease is determined by the prevalence and the pre-test probability of that individual. Because hypothetically, you could diagnose a patient by just looking at the patient and knowing the prevalence of the disease in your population. So I know that 30% of the population has diabetes, and I point at every individual. I pick a random individual out of my population. I have a 30% probability that individual has diabetes. We did that example, right? You remember the probability examples of alopecia, for example. So these are the examples that build up to this lecture, because essentially you have a probability before you even employ the test, and you employ a test, and then you have a probability afterwards, which takes those both into account. And that is positive and negative predictive value. Can be calculated if you have this 2x2 table. You essentially, you have now, if we recall, we have sensitivity calculated as true positives divided by true positives and false negatives. So that's 5 divided by 20. That would be 25. Then we have specificity is 18 divided by 20, specificity of 90%. Positive predictive value is calculated horizontally. So you basically you have the outcome. Here's columns. You only focus on the test now. So positive predictive value is what is the probability after using that test in a positive population. So if I have 5 divided by 7 would be a positive predictive value. So that's the true positive divided by true positives and false positives. Then I have the negative predictive value, that is true negatives divided by true negatives and false negatives. So that's 18 by 33, which is not a good negative predictive value, notably. Yes.
Like you said, the higher cutoff point will give us more of the positive predictive values, right?
Could you repeat the question?
Like if we have a higher cutoff point, we are going to have more of the positive predictive value accurately.
The cutoff value the positive predictive value should not be affected by the cutoff value. While you will, so the cutoff value determines sensitivity and specificity. So think of it in that way. This, which we discussed before, you have here a threshold, right? The threshold goes down, you will have more false negatives, right? You will have more diabetics that are not diagnosed as being disease positive. You will, on the other hand, you will also have an increase in your true, false negative, false positives. No, sorry. Hold on a second. Okay, so you lower the threshold, you get more false negatives, right? So you get diabetics that are being diagnosed as being disease negative because your threshold goes down. So that's your false negatives. Your false negatives would be these guys. You get true negatives because non-diabetics are basically not disease positive anymore. But what you also get is you get less true positives and you get less false negatives. So thereby, you basically, when you shift that down, you're also shifting this down. So you got to look at it. So this is literally, this is this 2 by 2 table in a way. So the positive predictive value should not change by changing the threshold.
If we reduce the threshold, let's say from 100 milligrams for our threshold, we reduce it to like 65. So we are going to get more false
Positives. Correct. And less and more false negatives. Less false positives and less true negatives. So this is where positive predictive value. So you really need to look at thresholds and this prevalence as shifting from here to here. And that will determine that basically within a test result, you're getting positive and negative predictive value. Because they're classified according to the threshold. But that will be a trade-off. And this is the debate that I mentioned before, right? So many screening programs have actually been very strongly debated. That included prostate cancer screening, that included breast cancer screening, teen screenings, it's also, so there was a time where CAT scans came up and like people do whole body CAT scans. So you're tremendously increasing the risk for false positives, which has ramifications. Not only is it the psychological stress, is also the risk of somebody basically just starting to schedule surgeries. And so there's unnecessary operations, and there's data, particularly in the Scandinavian countries, have been very strong in terms of public health to kind of be very conscious about screening and whether it actually is reasonable to screen and to act right away on the screening results.
So if we increase the quantity of screenings, we will increase also health results.
It's if you increase the screening frequency, you increase the screening efforts, you will almost consequently have more cases and consequently more treatments. Yeah, I think that's quite a solid association. Only a diagnosed disease is a good disease.
More accurate.
Yeah, but the question is, are you really more accurate because you're also increasing your risk of having false positives? That is the debate, right? That is the debate, and that is this trade-off. And this is, I am not standing here participating in the debate what should be done, but the debate is ongoing for many screening tests, right?
Maybe in this case, they just need to increase different tests, like not to repeat it, but just do different tests.
Yeah, so there's constant improvement, obviously. So if you, for example, look at the technology 30 years ago, so these articles are considerably from 2012, 2008. Like there's so much advancement in technology. The medical diagnostic, the industry, as well as medical diagnostics in hospital has gotten so substantially more improvements and has improved tremendously. It's like if you look at an MRI result from 30 years ago compared to now, it's like it's literally you're looking with a magnifying glass at it. Right now, it's like you really know what's happening. The resolutions have gotten better. Everything has gotten better, while the fundamental principle is still the same, but things have improved, but it became definitely more accurate in its prediction, but it still comes with the caveats that there still may be false positives. So it's not only improvement, it's sometimes also indication, it's prevalence. If you have preventive lung cancer screening, for example, in somebody who has been a 40-year smoker, yeah, makes sense. Does it make sense in a non-smoker? No, maybe not. Does it need to be done? Maybe not. Again, it's a controversy, right? It's a debate. It's a debate which is a public health debate, which is a healthy debate because it also costs money. Like in the US and a pay-for-service model, but again, there it's on the private sector. It needs to be controlled how much money you spend, right? In countries with socialized healthcare, it becomes a much more complicated conversation because then the taxpayers pay for all of this, right? So you want to minimize the costs as well. In countries with limited resources, what are you going to do there? There you need to basically really be very conscious about what you're doing, what screening efforts you do. So it's a complicated conversation.
It's the same like to show different doctors.
If you go to different doctors,
Different opinions.
well, but that's also a US principle, to be honest. It's like in Europe, I just had a recent conversation with somebody. It's here in the US, you can choose your physician freely, and you can also, you're almost like encouraged to get a second opinion, right? In many other countries, and I just had a conversation out last week at the conference I was, it's not very common in other countries. Let's put it that way. So there are substantial differences between healthcare systems. And the doctor alone, does it really make a difference in terms of diagnosis? Well, in some cases it may, in some cases it won't, may not. It's a tough conversation, but far beyond the scope of this class. But it's a good conversation. Thank you for bringing it up. So, but yeah, so this is why positive predictive value is basically of interest, right? So you want to have an understanding before you actually employ the test. What's the probability before I even use that blood test, that CT scan, or that X-ray? Yeah, so we talked about this last time. So we are now moving. So you have mutually exclusive probabilities. You have union of A and B. And today we're going to talk briefly about conditional A and B. And this is the principle that you have to employ. I used to do an arithmetic example walking through that, but basically conditional probability, this is what you're looking at with positive and negative predictive value. So you actually can quantify this by, I don't want to go too deep into this. You can look at this essentially by, so PA and this logical OR B will basically imply that the probability of A and B in the presence of over the probability of B alone gives you basically an overview of conditional probability. So this is merging the probability of an event occurring in the presence of a positive test in the knowledge of the pretest probability before you even employ this test. And I have arithmetic examples, and those of you that are interested, I can share some additional slides with you. But basically, what it comes down to, you're merging both of this information, and then you derive your post-test probability. And it comes back to the story I told you about Thomas Bayes, who was a mathematician and cleric from the 18th century. So he did this studies on a pool table where he tried to get with his blue balls as close to the red ball as possible without looking at the table, just rolling them backwards, and an assistant giving him an idea whether it was too far left or too far right, or whether it was hitting the ball. So basically, by having this additional knowledge of whether it was left or right, he was able to actually determine how to hit the ball. And he quantified this in, I don't know how many repeated experiments, and he was then arithmetically able to derive Bayes' theorem, which allows him to quantify conditional probability and basically build an algorithm to merge this and prove this. So you have here the probability of A. That is your pretest probability. You want to come here where you have the probability of A in the presence of B. So that's your post-test probability. So now you have the probability of A is the pretest probability, that's the prevalence. Now you have BA, that's the likelihood of an event occurring, which is essentially your sensitivity. That's testing in a population that has the disease to really test positive. And then you have PB, which is essentially your specificity. So you get by that, you basically get to your conditional probability. So yeah, so A before B is not the same as B before A. Okay. Yeah, so conditional probability determines that there needs to be condition met before you actually can move on to quantify the probability of B. these are the example that Dr. Warden had in there. So now employing this on the example we had in lecture in the first lecture. So we have treatment and control, and we have pain with mild pain, moderate pain, and severe pain. So we basically, so what is the probability of the group in the treatment? So what is the probability in that group of treatment? So we have group equals treatment. So we have the probability here of 15 over 20, right? So you get here a probability of 0.2, which is basically 15 over 30, 50. So this is 15 over 50. No. Where does it want to go with this? Okay, we can do this arithmetic examples then in Excel. You have a total of 100 patients. You have, it's 20 out of 100. Yes, yes, yes. But where does he want to go with this overall? I think it's smart. Yeah, we can do this example then another time. Okay. So application to a screening test, we did this, and this is basically where you draw the line then to essentially come to your post-test probability. So you have here a prevalence of 300 over 1,000, that's 0.3. We have a sensitivity of 294 over 300, which is 294 over the entire 300. We have specificity, which is 679 over 700. That gets us to 0.97. And now the probability of the positive predictive value essentially is now A over A plus B. So this is the 294 over 315. And negative predictive value would essentially be 679 divided by the 685. That gets us to a negative predictive value. So these are basically how you need to approach those. Make sure though, when you look at the 2x2 table, that you know exactly that row is the disease and that row is the test and the column is the disease. You see that sometimes in a different shape presented in some 2x2 table.
Prevalence is always more than 1.
It will be from 0 to 1, yes, because you only have 100% probability. So, and this is now the example we had from before. So you have here the probability of a true positive. So that's your post-test probability, which is basically your probability of a test positive in your positive chlamydia patients. So that's your sensitivity. That's the probability of chlamydia positive. That's your prevalence, plus your 1 minus specificity. So that's the false positive rate, plus 1 minus the prevalence, and that's basically your healthy population. So that's your denominator, your PB. That formula. So this basically gets you to the same positive predictive value that was calculated earlier. So now this example basically wants to guide you towards how important is actually sensitivity in this game. So when you have a prevalence of 0.3, you're basically quantifying here a probability of a true positive versus a probability of a false positive. So you have a chance of a positive test that is 93%. What happens if your probability goes down to 3%? Your probability of a true positive virtually doesn't change and doesn't really is strongly affected by the prevalence. And you see this here depicted down there by the positive predictive value. Whereas when you change your sensitivity, and this is that change here from 0.98 to 1, you basically have only marginal changes in your outcome. So it's really not about the sensitivity of a test. So changing this threshold changes the sensitivity and specificity. But really, it's the prevalence that drives your positive and negative predictive value. And that's the take-home message. So know the population you're testing. That's the take-home message. Okay. So we have with sensitivity and specificity, we have the properties of the test, whereas positive and negative predictive value, we have application of the test to the population. That's just the summary of the notation. Okay, any questions on any of this? All right. Then let's go towards the examples. Okay, so just as a quick explanation. Okay. So you have here. You have a paper attached that basically was conducted in a large cohort in Malawi. So basically, patients were screened for kidney disease. Patients at an increased risk of kidney disease were screened for kidney disease. Commonly, the most commonly used marker for kidney disease is the so-called estimated glomerular filtration rate, where basically you quantify serum creatinine. Creatinine is basically produced in the muscle, is a result of muscle activity and muscle mass presence. And in the presence of a decreased renal function, you will basically see an increase in creatinine. So you have the same muscle mass and you assume you have the same activity. So you see an increase in creatinine, which is then caused because it's not excreted. And oops, what is this? No, it's not good. So you're measuring this and you basically put this into context of age, gender, and that these models will basically allow you to estimate the glomerular filtration rate of the kidney, which is basically how much the kidney basically can clean from a toxin. So this is the most common way. The problem with creatinine is it's a little hard to measure, and we have worked, and it also requires access to the circulatory system, so you need to draw blood. So we have, in 2005, we came across, or colleagues came across, a saliva urea nitrogen dipstick. So urea nitrogen is produced in the liver. It's basically it's derived from protein metabolism. It's produced in the liver. It's basically it's the way of the body to take nitrogen and get rid of nitrogen out of the body, because nitrogen is a gas. If you wouldn't bind this in some shape or form, it would basically build gas bubbles and you would die of gas bubbles. That's a gas embolia. So you bind this together with carbon molecules and you form urea, which is solvable in water. It solves in water and it's basically excretable by the kidney. If the kidney doesn't work, it increases just like creatinine. So based on research from the earliest 20th century and even earlier, some reports even earlier, it was known that the saliva reflects the urea nitrogen of the blood. That means if the urea nitrogen in the blood is high, it's also high in the saliva. In veterinary medicine, they actually used, for the sake of drawing it and not having to draw a blood sample, they're using saliva of animals to basically diagnose urea nitrogen. The interest came up, and we studied it in a chronic kidney disease cohort in Austria. And we found that there's an association between blood urine nitrogen and saliva urine nitrogen also in humans. We then went on and studied it in different CKD population, in patients having acute kidney injury, in patients coming to emergency rooms in Malawi, in patients suffering from malaria in Angola. So we studied it all over the world, and we came up with kind of consistent results. This publication, one of the latest publication, and we want to look at this data now, and we want to use basically simulated data to create a scenario that kind of will to some extent resemble the values we have in there in the paper. And we want to use diagnostic methods to quantify the diagnostic performance of that test that we have at hand. So we're doing that. First of all, there is an absolutely fabulous way of quantifying diagnostic performance. It's called a receiver operating characteristics curve. And we're going to do this today. We're going to do a ROC curve. So those of you that have a little bit of a coding background, you have heard of an ROC curve, no doubt, because it's also used for testing the diagnostic performance of more fancy advanced analytics, and you can use it to determine whether a predictive model actually is predicting what it's meant to predict. And that's the context that's being used. It's more commonly used also in diagnostic and medical diagnostics, and this is where we're going to look at it today. Good. For the purpose of this ROC curve, we need to load the library PROC, which is line 2. So let's just start off with this line. You need to install the package first. So please go on packages, go on install, and write PROC, and you will find the package PROC. Install this on your R, in your R Studio. I hope no more R tools issues. And then run line 2, which basically is the library command, which will allow for you to activate the package PROC. Good. Line 5. Line 5 builds a data frame that consists out of two different, yeah? Good. Okay, line 5 consists out of various components. So basically, it creates two different. It builds two different variables. One is patient ID and one is EGFR. So you know, patient ID here was 1:649. Basically, creates a consecutive vector of 649 entries, 1, 2, 1, 2, 3, 4 until 649. Our binom is basically creating 649 entries of zeros and ones with desired proportion of 0.77. Why 0.77? Because this is as per table 2. I think it was 2, no? Table 5, sorry. This is as per table 5, the number of we're looking at where did I come up with 77%? So these are the 649. We are quantifying now the 17.7% of oh no, here. Yeah. Oh yeah. So we are quantifying these 649. So it's actually okay. So now I'm back on my. So we're presenting with an eGFR smaller than 30 milliliters per minute per 1.73 square meters. The prevalence of the disease is 17.7. So this is what we mean to reproduce. So what we're doing here in line 5 is basically we're quantifying a data frame that has 649 entries for 649 patients. And these patients either do have a diagnosis of a disease or don't. And this is what we're doing with our binom, where we're basically assigning zeros and ones randomly to our 649 patients with a proportion of 177. And this is happening in line 5. Line 6 essentially is doing nothing else but counting our entries of eGFR 30. So this is counting that second row. So we have 111. All of you have different numbers because it's simulating it differently on your end. Yeah. Okay, it's different. So 115 is what Reese has reported in his paper. And I have 111 other entries. 114, okay, good, close. So this is a random generator, right? We're simulating data. It doesn't really matter. So now we have now we're going a little further. Now we have now a second parameter where we're seeing DF-SUN, saliva, urine, nitrogen, SUN negative. Where this equals 0, we're doing our binom length of exactly that entry. So this is all where this was actually 0. So now we're creating our false positives. So we have now 1 minus 0.846. So we have now some negative 1 minus 846. 846 was here. 846 is our specificity. So if you have specificity, you're quantifying the true negatives out of true negatives and false positives, right? So these are the ones that don't have the disease. They tested negative, those are the true negatives. And then those that tested positive, those are the false positives. So we are quantifying now 1 minus the specificity. So that's our false positives. That's the false positive rate. So we're quantifying here in SUM positive, we're quantifying here those. We're reproducing our false positives and true negatives. Make sense? Think of it that way. And let's actually do this with. So we have here disease. So KD for kidney disease, positive and negative. Now we have here test. So that's SUN, positive and negative. So these are our true positives. These are our true negatives. These are our false positives, right? And these are our false negatives, correct. So now 0.846, which we're quantifying now, is this group, these out of these two. That is 0.846. These true negatives. So now if we do 1 minus 0.846, these are these guys. So these are these guys. So we're quantifying now these as being those that are positives but shouldn't have been. So this is why we're doing now a different command. We're saying length of those where EGFR was 0. So that's the right column. And we're saying, okay, so give a 1 with a proportion of 1 minus 0.846, and the other one makes 0. Those are the true negatives. The zeros are true negatives, and the ones that are 1, those are the false positives. Make sense? And we're doing this randomly. It's a fun little simulation exercise, right? So whenever you think of that code in a way, if you want to in any way kind of test something and you want to play around with sensitivity and specificity, that's how you can do it. It's not, it's that there are more sophisticated approaches, right? I'm making it extra simple because I want you to go through that learning step with me, the thought process, because that's how you internalize. That's how you internalize what sensitivity specificity is. Okay, so at the end of the day, you're running line 7 and you're creating the sum. You have a 0. That's not good. Okay. It's still 0. Why is it 0? Let's try to quantify this. Oh, because it's okay. Okay, you need to change line 9 to SUN negative. Sorry for that. So this was SUN positive, but that should be SUN negative because that's what they defined in line 9, not some positive. Yeah, so change, so if you run line 7, you get this randomly generated false positive, true negative. In line 8, you get sum of DF SUN negative. You get the sum. That should be somewhere in the realm of like 72, 74. Okay, line 9. You get what?
Yes.
Okay, line 9, you're basically designing now the left column. We have now true positives and false negatives. You know that the sensitivity is a number that I've forgotten, but it's somewhere in the realm of like 90 something. So you basically want to quantify these and these. These are the ones with the 1. These are the ones with the 0, right? This is diagnosed positive or not. So you get here 0.661. 0.661 is yeah, 0.661. So you're getting now a sensitivity reflected by true positives over true negatives and true positives and false negatives. Here on line 9 and line 10, you get 78 true positives. So all were SUN.
That's 0.
SUN, did you change SUN positive for SUN negative in line 8?
8.
8. Yeah.
Yeah.
Then just start from scratch again. Start from line 5 and go step by step down. So line 11. Line 11 basically creates now the following. So now you want the actual SUN value. So the SUN dipstick is yeah. the SUN dipstick, that's essentially how that looks like, that thing. So this is the dipstick. So this is it comes in a little bottle. You have 50 in a bottle. Each of these dipsticks costs like $1, and you can save kids' lives in developing countries with this. I still believe in this dipstick. So you take saliva samples and you have a semi-quantitative assessment. You basically you will have saliva that will be applied on the test bed. There's a chemical reaction that basically turns a pH indicator green. So the greener it gets, the more positive it is. So the higher the concentration of urea nitrogen in saliva. The greener it is, the higher the assumed blood urea nitrogen. But it's 6 dipsticks. So you have six different possible values this dipstick can change it. It's actually it's a spectrum, but the categorization was 6. We opted for categorization, and we kind of did some experiments, and we kind of came up with ranges. So this is how this thing looks like. That's the chemical reaction. So now we need to classify in our simulation. We need to classify now the individuals into 6 different categories. We know from previous studies that everything greater than test bed 1 is kidney disease positive. So this is what we're doing now. So we're saying now SUN, where SUN is positive, equals 0. So that's the lowest. This is where we see, so we're coming the other way around. So the SUN diagnosed it as negative. We know that from Rees' paper. Now we're diagnosing this as test bed 1. So that's line 11. Line 12 is now basically taking SUN positive 1. So the SUN was positive, so it needs to be somewhere between 2 and 6. These are the leftover test beds. With the sample command in line 12, replaces true, we're basically creating now a sample that will basically have the length of all the positive ones. So we're just sampling randomly 2 to 6s through. And this is what line 12 does. That's not good. That's not good. What now? Yep, I know, that's an error. And is not allowed in subscripted assignments. What does that really mean? Sample 2 to 6. Let's see, positive lengths. So this is the problem if you try something for the first time with a class, and that doesn't work. 595. Sample. Subscripted. NA is another that is subscripted. Bear with me for a second, please. I apologize. Okay, we need to improvise here. I don't know why it doesn't work. It worked at home. Okay, we're changing now line 12. Line 12, we're changing the whole sample command to 2. It doesn't make a difference whether it's 2 to 6 or it's just 2, right? So we're just overriding it all with 2. Okay, improvisation is half of the life. Okay, so we're overriding with this 2. So now we have the factors on line 13. Look at this. That's the issue. Hold on. Sun positive equals 1. Okay, that is an epic fail. Okay, quick revision here. I am uploading a new spreadsheet, a new R code on Canvas. Oh no, I sent it as an announcement. This event. Sorry for that. I apologize. This is it worked, or at least I thought it worked. Please download the code that I've just uploaded as an announcement. Practice Lab 4 is labeled the same way. You just have to override and load it again into R. Sorry for that. So what happened is it subset it wrong, and it would fail with the population of what I wanted it to populate. It's annoying. Yeah, but now we can't build our own. It's still suboptimal, but we can continue at least. I will upload an updated code tonight. I need to look into the sample function. Something went wrong there. Okay. So we have now 579 individual, 570 that are negative. We have 79 positives. We can now categorize them, and we categorize them with line 18 to line 24. This is basically, so it basically takes each of R1 equals 1. So that's basically disease positive, test positive. Disease positive, test negative. Disease negative, test positive. Disease negative, test negative. So it basically categorizes them. And with line 23, you're basically getting now this transformed into factors. Know how to handle factors, because factor, again, missing values. This is, so you basically with the factorizing values, you get these assigned to the respective categories, and then it will be easier for you to build a summary. So know how to do factors. We did factors in previous classes, so you know how to do factors. So if you're quantifying now the length, you can now quantify, everything is acting out. Oh, come on. You can calculate now sensitivity, and we only can do specificity and negative predictive value, which is basically now consistent with the values that Rees has reported. So negative predictive value is here somewhere at 0.91, specificity at 0.87. So that should be depicted here. Sensitivity and positive predictive value didn't work out because, for obvious reasons, because my code didn't push through. So sorry for that. This is really so annoying. And then here the ROC is also not going to work. Well, it does work. Okay, it does work. It does work good enough, but it's only 1 and 2. So let's look at actually at Rees's. So here's a much nicer one. So an ROC curve is the curve that you see here. This is basically showing you, so this is the ROC curve that we should have seen. What does the ROC curve show you? Yeah, you have a question? An ROC curve gives you a graphic overview of, and this comes back to your question on how do you determine this trade-off between sensitivity and specificity, or was it your question? I forget. The trade-off between sensitivity and specificity. You have here on the y-axis, you have sensitivity in percent or as proportion. And you have here on the x-axis, you have 100% minus specificity. Remember, 100 minus specificity. Specificity is the proportion of true negatives over true negatives and false positives. So 100% minus specificity is your false positive rate. So these are your false positives. So now what you want to create is, so this is basically a graph of the probability of a diseased population being diagnosed correctly as a function of false positive, the probability of false positives. So you see this mapped out here from 0 to 100. So you basically see that when the sensitivity is increasing, that's the capability or the probability of disease, of diagnosing a deceased individual accurately, correctly. but it also will lead to an increase in your false positives. And this is where that trade-off goes. So you basically have an increase in sensitivity, and subsequently your false positives will also increase. They have to. So now what you can do now with this trade-off, so first of all, if you have the quote-unquote line of identity, this line of identity, this red line, indicates a diagnostic test that is equivalent to flipping a coin. That's a 50% probability. So that's like flipping a coin, okay, you have cancer or not. So if you have now quantified everything, so these 50% you have under the belt, so this is there. You need to top this. And topping this essentially you do with that function that spans here as a function of sensitivity, as a function of false positive rate. Everything under this function, so this area under the curve, is quantifying your diagnostic performance plus 50%. So you essentially, you want to have your area under the curve, which is, well, it depends on what your thresholds are. Here was somewhere in the realm of like 0.8. You want this to be higher than 50%. You want this to be as high as possible, somewhere between 50 and 100, as close to 100 as possible. And at the very least, you want the 95% confidence intervals not overlap your 50, because that means like it's barely or not even better than you're flipping a coin. So that's kind of how you quantify the diagnostic performance of the test. So it's sensitivity as a function of the false positive. Any questions on that? And then it really just comes down to what are you defining as being diseased? So that's the outcome definition. What is also important, so this was a dipstick that has 6 different test beds. These points are the test beds. And they basically represent different trade-offs. They represent different values a marker has been able to take on. So if this were a continuous measure like blood glucose, these were continuous measures all across. And then the threshold that you use to diagnose a disease is something that you can determine based on the shape of this function. So what you often see is like you see something that increases sharply and then goes flat. And then you know that junction point, that is that value that you really want to use as a threshold. So the shape of the function informs you of how well is your test working at different levels. So this comes back to what's that trade-off point that you want to use to determine, because if you have little gain of increasing that threshold, but losing specificity in exchange, you may not opt to do that. So you're not sacrificing specificity, taking a larger risk of false positives for an increase in sensitivity. So this shape informs you on how to determine your threshold. Okay, any questions? ROC curves are really cool. I will work on that code. I sent you an updated code out. Apologize again for the mishaps. I don't know how that happened. It seemed fine when I looked at it, when I programmed it last weekend. But then you can play around with your own ROC curves. And you can look at different functions, so there are different additions. Also, what I wanted to make as a parenthesis, if you are interested, so if you look at this output here, you actually see here the area under the curve quantified, So that's the area under this function. You see here the 95% confidence intervals. And you can, in addition to that, you can always, with the question mark, ROC, for example, ROC, with the question mark, you always get to see the package manual. So you get an actual explanation of the function. At least I hope this is going to happen at one point. Oh yeah. So you gotta click here on help. So question mark and the function name gives you here on the help tab. It gives you here a very detailed description of the function. So you can read up on the function. That is very helpful. Gives you also examples. So at the very end, you have here examples of how to quantify things, and you can play around a bit more with it. All right. Okay. Any questions? The ROC. Yeah, I have. You could not find function is a question of this. Yes, it was on this. So now it should work. Yeah, so you don't have levels because my code failed. I give you an updated code and then it should work. Okay. So the function works now. Yeah. No, I need. Is this the new file already that I uploaded?
Yes.
Okay. Yeah, I need to send an updated file. My apologies for that. That's it's just annoying. My mistake. All right. So if no further questions, then thanks for your attention and see you next week. Make sure to study for the quiz. Can be fun.